Hey everyone, welcome into lecture number 18 of linear algebra. This lecture is on diagonalization, and let's start with a theorem. So the theorem that we're going to use today says the following. So if lambda 1 through lambda k are distinct eigenvalues, so this is important that they are distinct, meaning different, right? So distinct eigenvalues of an n by n matrix A, and they have corresponding eigenvectors. So we have corresponding, or I guess corresponding is the correct term here. So corresponding eigenvectors x1 through xk. So since they're distinct, then these are individual eigenvectors for each one. Then the eigenvectors are linearly independent. All right, so the eigenvectors of these distinct eigenvalues are going to be linearly independent. So let's sketch the proof here. I'm going to just write proof, but I'm going to maybe not show every single detail. But the basic idea of the proof is to assume that some of the vectors are linearly independent, but then if you add one, that they become linearly dependent, and then to apply A to the mix, so the matrix A. So here's what we're going to do. Let's assume that x1 through xr, where r is less than k, assume that the first, so in some sense the first r of these eigenvectors, and honestly the order doesn't matter, but let's just keep them in the order that they were given in. Again, that's what I'm saying. This is just going to be a sketch of the proof. But let's suppose that the first r of these are linearly independent, but if we add one to the mix, so x1, x2 through xr, and then add the next one, xr plus 1, which we can do because we assume that r is less than k. So at this point, if r was k minus 1, then we've got xk here, right? It's the last one. Assume that these ones are linearly dependent. All right, so what does this mean, right? So let's review some of these definitions that we maybe haven't used in a while. But what this means then is that there exist constants C1, C2 through CR plus 1, not all zero, right, such that the linear combination C1 x1 plus C2 x2 plus, and by the way, well, I'll say this in a moment, but CR plus 1, let's write the previous one as well. So CR XR plus CR plus 1 XR plus 1, that this is going to be equal to the 0 vector, right? And these constants are not all 0. Remember also that because these are eigenvectors, right? So since these are eigenvectors of the matrix A, then the eigenvectors are not 0, right? So the vectors themselves are not 0. So what does this mean? I'll just write recall that the xi are not equal to the 0 vector. And so thus what this means is because we assume that the first r are linearly independent, then this means that CR plus 1 has to be non-zero. Because if CR plus 1 was 0 and this equation was satisfied, then it would mean that the first r are actually linearly dependent, right? So there would have to be a non-zero one of them, right? We assume that they're not all 0. So if CR plus 1 is 0, that means one of the other ones is non-zero, right? Which is not allowed. So basically the whole point here is that CR plus 1 is not equal to 0. Okay? Now, so I'm going to call this equation star. What we want to do next to this is apply A to this whole mix. So multiplying by A, what do we get? Well, multiply this whole thing by A, right? A is going to hit each one of these. So I'm going to write it out, I'm going to distribute the A through. We know that we can do this, right? Everything is linear here. So we multiply through by A. We get C1AX1 plus C2AX2 all the way up through CRAXR plus CR plus 1 AXR plus 1 equals 0. A times 0 is 0, right? Now, because we've assumed that these are eigenvectors corresponding to the eigenvalues, right, distinct eigenvalues, then the a times x's can be replaced by constant times the x's, right? So this becomes c1 lambda 1 x1 plus c2 lambda 2 x2 all the way up through cr lambda r xr, and then cr plus 1 lambda r plus 1 xr plus 1 equals 0. And so now what we want to do is go back up through, so I'll call this equation 2 star. All right, so then multiplying equation 1 star by this eigenvalue lambda r plus 1, and then subtracting. So what we're going to subtract is going to be equation 2 star minus lambda r plus 1 times equation 1 star. We obtain the following. All right, so what do we obtain then? It's going to end up being c1 times, so the way that we've arranged this is going to be lambda 1, so the c1 is going to factor out, right? We're going to get lambda 1 minus lambda r plus 1, which is non-zero, times x1, plus c2 lambda 2 minus lambda r plus 1 x2, etc. all the way up through CR. Notice the last term is gone, right? Because when we multiply lambda r plus 1 by this equation 1 star, then the last term is going to be exactly the same as this term, right? In 2 star. And so down here what we end up with is linear combination CR lambda r minus lambda r plus 1 xr equals 0. And these lambdas are distinct. Lambdas are distinct, so these differences are not 0. And therefore, when we add this all up, right, the x0 was not 0, or none of the x's are 0. And so this now contradicts. This contradicts the assumption that the CRs are linearly independent. Okay, that the CR, the first R, are linearly independent. And so therefore, we have reached a contradiction. So this contradicts the assumption. And that's because since CR plus 1 was non-zero, right, then one of these must also be non-zero, because otherwise you'd end up, none of the vectors are 0 either, right? So this contradicts the assumption that the x1 through xr are linearly independent. All right, so what's the conclusion then? Well, the conclusion then is that actually what's the contradiction to, right? The contradiction is to that, but the conclusion then is that our assumption that these x1 through xr plus 1 are linearly dependent, that is wrong, right? And so therefore x1 through xr plus 1 must be linearly independent, right? And this is true for all r less than k, and so when you make r equal to k minus 1, then you get all of them, right? And so that's it. That's the proof. All right, so the whole point here, though, let's go back and read the theorem again, is that if you have if you have a matrix with distinct eigenvalues, then the eigenvectors of those eigenvalues are linearly independent. All right, so that's the big deal here. That's the takeaway. So the distinct eigenvalues lead to linearly independent eigenvectors. Okay, so now let's give a definition. So this lecture is called Diagonalization, and so far I've just talked about eigenvalues and linearly independent eigenvectors. So let's give our definition now of diagonalization and a diagonalizable matrix. So we'll say it this way: an n by n matrix, square matrix again. We're still doing eigenvalue, eigenvector stuff, so it's not a surprise that we're working with square matrices here. But an n by n matrix A is said to be diagonalizable if and only if there exists two matrices, but really one major one here. But if there exists a non-singular matrix X, Non-singular meaning the columns are linearly independent, right? And a diagonal matrix, which could be singular, but a diagonal matrix D, such that the following is true. So the definition is the following. It's that x inverse times A times x is equal to that diagonal matrix. That's the diagonalization of A. So x inverse times A times x. All right. Another way to write this is, of course, that A times x is equal to x times D, right? So just multiplying x on both sides here, on the left-hand side of both sides of the equal sign. And in this scenario, we say, but then obviously the right-hand side is no longer diagonal, right? So this definition is to isolate the diagonal matrix. That's the reason for writing it this way. But we say that x diagonalizes A. All right, so now in this scenario, so if this is possible, then it would be really nice to be able to find some general form of the matrix X and then the matrix D as well, right? So let's do a little observation here. So let's just observe. So let's say if this is true, right? So if A times X equals X times D, then let's take a look at both possibilities here, both sides. Remember, X is a non-singular matrix. It's not really super important for what I'm about to write down, but it is important though. So let's not forget it. So if AX equals XD, we can write X as a row vector of its column vectors. We've done this many times, right? So X is x1 through xn. Those are the columns of X. And then we can multiply on both sides of this matrix, right? We can work out both sides of this. So in one hand, A times X is equal to A times this row vector of its column vectors, so x1, x2 through xn. And then we know that A just distributes into there, right? Because A is an n by n matrix. These are n by 1 vectors. And so the products are columns of A times X, right? So AX2 all the way up through A, xn. On the other hand, X times D, well, this is our row vector. So x1, x2, xn times D. Well, D is a diagonal matrix, right? So D is going to be D11 zeros, 0D22, right? And then etc. So DNN, and then all the rest are zeros here. And when you multiply this out, look what happens. So as you just do like a row vector times this matrix, right? As you go through it, you're going to see that all you end up with here are x1 times d11. So I'm going to write it as d11 x1, because at that point d11 is just a constant. The second entry here is going to be x2 times d22. So again, d22 x2, all the way up through dnn xn. And so now we compare, right? So look at the entries. We've multiplied this two different ways. These are supposed to be equal to each other, right? These are supposed to be equal. So we see the first entry tells us that AX1 has to be equal to D11 x1. Okay. AX2 has to be equal to D22 x2. And this should be setting off alarm bells in our mind, right? Because the D11 and D22 are constants. The X is a vector. A is a matrix, right? And so what we conclude, just by comparing this, you can go through the rest of them as well, right? It's got to be true for all of them. So what we conclude then is that A times xi has to equal dii times xi. Well, this can only happen, right, if the xi's are the eigenvectors of A and the dii's are the corresponding eigenvalues of A, right? And so this is our conclusion, right? So the xi are eigenvectors of A, and these dii equals lambda I are the corresponding eigenvalues. So the diagonalization is basically built out of a matrix of eigenvectors, eigenvectors of A, right? And then the diagonal matrix is built out of the eigenvalues of A. It's built out of the eigenvalues. So we can summarize all of this in a theorem now, and so we will. The theorem says the following. So A and R, n by n, is diagonalizable if and only if, so A is an n by n matrix, right? So if and only if A has n linearly independent eigenvectors. So Li here means linearly independent. So in other words, if the eigenspace of A is all of Rn, right? The eigenspace, the eigenspace is plural, right? So if the union of all the eigenspaces is all of Rn. Maybe that's not the best way to say it. Maybe it's better to just say if and only if A has n linearly independent eigenvectors. All right? So we will take advantage of this as we move forward. But before we do examples, I want to give another definition here. So what I want to talk about now are powers of diagonalizable matrices. So now a diagonalizable matrix is going to be one for which we can write it out. So it's going to be the same as, right, a matrix whose eigenvectors has n eigenvectors that are all linearly independent. So powers of diagonalizable matrices. Here's how it's going to work, right? So if we have the following, so if we have x inverse A x equals D, then we can also write A is equal to x D x inverse, just multiplying everything through. So x on the left, x inverse on the right. Then we can write this where D is a diagonal matrix. And then we can take the powers of A, right? So then we can write then A squared is equal to x D x inverse times itself. So times x D x inverse. And at this point we see, all right, x inverse times x, that's just the identity matrix. And we know that, I times D is just D, right? So this ends up being x times D squared times x inverse. But D is diagonal, right? D is diagonal. So look what happens here. Since D is diagonal, then D squared is actually equal to just the diagonal matrix whose diagonal entries get squared. All right, so we just square those terms. So it's very simple. It's the same matrix X, right, times, it's still diagonalized, right? It's diagonalizable, I guess, in some sense, but it's diagonalized by X, so the A squared is, and the matrix of the diagonal matrix in the diagonalization is just the matrix who, in this sense, the eigenvalues are the squares, right? The squares of the eigenvalues. And so what we end up with then is that actually any power of A is going to obey the same rule. So A to the power n is going to equal x times D to the power n times x inverse. So we get the same exact situation here for any power of n. We're going to say for any integer n greater than or equal to 0. And so what we'll regard here, I'll say this one more time here, but regarding A to the 0 as the identity matrix. Just like anything to the 0 power is equal to 1, right? So the diagonal entries to the 0 power will be the identity matrix. Okay? Now, here's what we really want to do with all this. So now we know how to take powers of diagonal matrices. So now I want to, or powers of diagonalizable matrices. Now what I want to do is define the exponential of a matrix. So before we write down the definition of the exponential of a matrix, let's recall the power series expansion of e to the x. So the function e to the x. So this is given by the following, right? So e to the x is given by power series expansion n 0 to infinity 1 over n factorial x to the n. Right, so this is 1 plus x plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4th plus 1/120th x to the 5th, etc., right? And so this continues on. So that's the power series expansion of e to the x. The exponential itself doesn't make any sense for a matrix, but everything on the right-hand side here does make sense, right? Constant times a matrix, matrix squared, all that makes sense. And so we can extend this, right? So we extend this definition the power series definition to matrices. And we write then e to the power a is equal to the sum, n goes from 0 to infinity, 1 over n factorial a to the power n. And so in terms of our matrices, the only thing that's going to change is the 1 becomes an identity. The next term is the matrix A itself. The next term is 1/2 a squared. The next term is 1/6 a cubed, etc., right? It just keeps on going. And so we get a series of a sum, right? An infinite sum of matrices here. And we can ask if that converges or not. So obviously it'll converge if every component converges. So it's component-wise convergence, actually, because that's how addition is defined, right? Component-wise addition. All right. The key thing here, though, is that if A is diagonalizable, then remember, A is equal to x d x inverse, and we just worked out that a to the power n is x d to the power n x inverse. And so if we just plug into this definition, we plug in our formula for d, right? Then look what we get. So e to the a is then going to be all of this, right? So I'm going to write it out I'm going to skip some of it and just write it out in terms of the d over here, right? So it's going to be I plus x d x inverse plus 1/2 x d squared x inverse plus 1/6 x d cubed x inverse plus 1 over 4 factorial. I'll write it as factorial. X d to the 4th x inverse, etc. And we can see exactly what's going to happen now as long as we write this right here, this identity matrix, as xi x inverse. Then we can factor an x out to the left of all of these and an x inverse to the right of all of these. And this can be written then as x times I plus d plus 1 over 2 factorial d squared, 1 over 3 factorial d cubed, etc. x inverse. And this is, of course, equal to x e to the d x inverse. All right. And it turns out this is it's going to be an exercise, but a recommended exercise for now, where it turns out that because d is diagonal itself, right? Then e to the d is the matrix whose entries are e to the d11, e to the d22 along the diagonal, down to e to the dnn, zeros everywhere else. All right, so we can compute the exponential of a matrix A by finding its diagonalization and then just doing a little bit of very simple arithmetic here, right, to compute this. So the e to the d11, etc. Yeah. So if A is diagonalizable, then we can just use this formula right here with these two very simple definitions here. So if A is diagonalizable, we can use this method. If not, we have to use the definition. We have to actually compute the powers of A. All right, so if not, we must compute all of the powers of A. All right, let's do a couple of examples here, and then we'll leave this lecture here. So for this one, we'll do the following. I'm going to leave a lot of the work here for you, but I'm just going to show you how this works. But let's say, all right, A here is the matrix 3, 2, 2, -1, 0, -1, -2, -2, -1. All right, so at this point, I'd like you guys to just pause the video quickly and try to work out the eigenvalues and the eigenvectors of this matrix. What you will get, so take a moment now and pause and work those out. But what you will get are the eigenvalues here are going to be 0, 1, 1. So in other words, 0 and 1 happens twice. And then the eigenvectors that correspond to these. So the eigenvector that spans the null space here is going to be 1, 1, 1. You know it's the null space because 0 is an eigenvalue. And then the other two have, it's an eigenspace of 2 dimensions actually. And so you end up with 1, 2, 0 and 1, 0, 1. As long as these are linearly independent, you don't have to check with this because of our theorem, right? So you just have to make sure that you find linearly independent basis vectors of the eigenspace for lambda equals 1. But you get this, right? And so at this point, this means that our matrix X is built out of these. So now we have to keep these eigenvalues in this order, 0, 1, 1. All right, 0, 1, 1. And then we can just build our matrix X by kind of putting together these eigenvectors. All right, and by the way, eigenvectors are not unique, right? So you could have a very different matrix X here, but your matrix X will be non-singular because your eigenvectors will be linearly independent, right? And so for the way that I've written these down here, what we'll get then is that our inverse matrix, X inverse, is going to be then -2, 1, 2, 1, 0, -1, 2, -1, -1. So you can do this by the cofactor method for the inverse, right? And then what we end up with is that A is going to be equal to the matrix X times diagonal matrix whose diagonal entries are the eigenvalues. Whoops, that's a 0. So it looks like that. There's our diagonal matrix times the inverse matrix over here. All right. So this is our X, D, X inverse. And now if we wanted to take the exponential of A, then we can do it, right? So further, e to the A is going to be equal to X, and X inverse stay the same. So these matrices stay the same. This becomes e to the D. But remember how this works. We just take the exponentials of the diagonal entries alone. So e to the 0 is 1. E to the 1 is e, right? And so there's our e to the D. That one's simple, right? And then we just write down our X inverse, which we've already computed. So in terms of the factorization here, it's very simple to take the exponential of the matrix. But then after a little bit of work, you can combine this into a single matrix, right? And so what we end up with, I'll just give you the answer. But again, you can pause the video and work all this out and make sure that you can compute the same answer here. What you'll end up with is a matrix whose first column is 3e minus 2, 2e minus 2, and 2e minus 2. That's the first column. The second column is 1 minus e, 1 minus e. And the third column is 2 minus 2e, 2 minus 2e, and 2 minus e. So that's the exponential of the matrix e to the power a. Really, e to the power a doesn't even make any sense, right? We defined it by the power series definition of e to the x, and then we just use the same notation that we use in calculus because it's easier than writing out the whole power series. But the exponential of a is given by that. Okay, so there's one example. One example, probably enough, honestly, because they're all going to be the same at this point. As long as your matrix is diagonalizable, your job is to find the eigenvalues, find the corresponding eigenvectors, and then just plug them into the proper positions in your diagonalization. But let's do one more example here where we try to find the exponential of a matrix that is not diagonalizable. So here's an example of a matrix that is not diagonalizable. I'll let you check it, but whoops. First column is 0, and then 1, 0, 0, 0, 1, 0. All right. By the way, a matrix that is not diagonalizable is called defective. It's kind of a weird definition, but it's called defective. So let's just write out some terms for this. We have our matrix a to the 0 power is going to be I. So you can check, by the way, that this is not diagonalizable, but we're going to find out very quickly that it's not. So, but for the sake of this one, let's just use our definition. So e to the a is going to be I plus a plus 1/2 a squared plus 1/6 a cubed plus 1 over n factorial a to the n, etc., right? So this is what we're going to compute. Now, a to the 0 is always the identity, A in this case is that, right? So I'm going to write it down, but by the way, the identity, we know what it is, but let's write it down. There's our identity. And then A squared is going to be A times A. So this one is going to be, if you work this out, you're going to find that everything is going to be 0 except for row 1 times column 3. That's going to give you a 1. Everything else is going to be 0. So this is our matrix A squared. All right. A cubed is then going to be what? Well, it's going to be the matrix A times the matrix A squared, right? So there's A times the matrix A squared. So A cubed, and now you work this out and look at, there's nothing in the first column. The only thing that you're going to get is in this first position. This is going to be the 0 matrix. You can work it out, but it's going to be the 0 matrix. If A cubed is the 0 matrix, then actually what's going to happen? Well, A times N is going to be the 0 matrix. I'm putting a vector symbol on it, but it's a 0 matrix, right? For all N greater than or equal to 3, actually. And so what does that mean? Well, it means in our expansion up here, all of this is going to be 0. 0 matrix, right? 0 matrix times anything is the 0 matrix. You add up a bunch of 0 matrices, you get another 0 matrix. So in reality for this one's not diagonalizable, but actually the exponential of this matrix is just the sum I plus A plus 1/2 A squared. So let's write that out. So e to the A for this matrix A is I plus A plus 1/2 A squared. So that's our matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, plus our matrix A plus 1/2 plus 1/2 times the matrix A squared, which is just going to put a 1/2 in this 1, 3 position. And then when we add this all up, we get 1, 1, 1/2, 0, 1, 1, 0, 0, 1, right? And so there's the exponential of this matrix, matrix A. So the exponential of this matrix is this one. That's e to the A. All right, now this wouldn't have worked. Again, it's a recommended exercise, implicit exercise for you to check that this matrix itself is not diagonalizable. It is defective. So defective in the sense that it does not have n linearly independent eigenvectors. Okay, and it will not. So you can check, you can find the eigenvalues, find the eigenvectors, and you will find that this is defective. It cannot be then, we cannot use the method that we used on this previous one to find the exponential of it. We just have to use the definition. But one of the benefits of this defectiveness is that actually we only need the matrices A and A squared, A cubed, and beyond are all 0 matrices, right? Okay, so this is an introduction to diagonal matrices. I'm going to leave this here, and I'll talk to you guys in the next one.